In this section, we are going to learn about different strategies we could use to graph surfaces in 3 dimensions. And we're going to focus on a particularly important kind of surface called a quadric surface. Quadric surfaces are the 3-dimensional equivalent of conic sections. Let's define it. A quadric surface is the graph of an equation that can be written in the form ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals 0. Okay, kind of long, right? So first off, notice how this really does extend the idea of conic sections, right? If we got rid of the z's, anything with a z in it, then this is just the general formula for a conic section. So this is the natural 3-dimensional extension of a conic section. The highest power is power 2. We just have 3 variables instead of 2. Okay. As with conic sections, most of the time we are going to look at these with these terms equal to 0. These terms end up rotating the quadric surfaces, and we're most of the time not going to worry about that. Okay. So let me give you some examples of what these quadric surfaces look like, and you're going to see that there's a large variety of these quadric surfaces. Now, unlike in with conic sections we kind of memorized all the different possibilities in their standard forms, right? With quadric surfaces, there's enough of them that it's a little bit impractical to memorize. So we're going to learn other strategies for approaching these quadric surfaces that can also apply to other surfaces. But I want you to see the variety that's available here. Notice as I go through some of these that the cross sections of these tend to be conic sections. That's going to play a big role to how we approach graphing these. Okay, so let's start with the first one here. This is, of course, a sphere. Nice, easy, simple quadric section, or quadric surface, rather. Okay, if you stretch it out a little bit in each direction, you get this. This is the 3-dimensional equivalent of an ellipse. It's called an ellipsoid. This is an example we've seen before. It is a cylindrical surface. It is a parabola in the YZ plane. But then there's no, if you look at the formula, no reference to x, so there's no restriction on x. So it stretches out in the x direction along the x-axis. So this is a parabolic cylinder. This is a paraboloid. This is a cone. If you want to be real technical, it's an elliptic cone, although the cross section from above is a circle. But we can change the equation so that it gets squashed in one direction or another so that the cross section from above will be an ellipse. Notice that just naturally the equations work out so that you get a double-ended cone, right? This is a hyperboloid of one sheet. You could kind of see the outline of a hyperbola in that hourglass figure, right? And then from above, in this example, it's a cross-section of a circle again. As before, if we stretch things out in different ways, it could be an ellipse instead of a circle. Okay? So that's a hyperboloid of one sheet. Now you may be asking, why is there a hyperboloid of one sheet? Is there hyperboloids of a different number of sheets? Yes, there's a hyperboloid of two sheets. Again, you could see that hyperbola cross section. Okay, but now there's two sheets because there's two different pieces. And then there's this guy. This is a hyperbolic paraboloid. Okay, you could kind of see, if we look at it straight on, the outline of a parabola this way. You could see, if we look at it straight on here, the outline of a parabola this way. And if we look at it from above, you could see, if I can get it, there we go. You can see the outlines of hyperbolas. Okay, so put that together, you get a hyperbolic paraboloid. So our strategy going forward is we're going to use those outlines, those cross sections, to help us get an idea of what kind of surface we're dealing with and to help us reconstruct the surfaces. So how are we going to graph these surfaces, like these quadric surfaces? There's a lot going on here. They're kind of gnarly, a lot of variables. How do we approach this? So as mentioned earlier, what we're going to do is we're going to look at cross sections. And that's going to make things easier, because once we take a cross section, that limits what we're looking at to a 2D cross section. We're better in 2 dimensions than in 3 dimensions. So if we can only look at 2 dimensions at a time, that'll help us. We give these cross sections a special name. We call them traces. A trace of a surface is the 2D cross section generated from the intersection of the surface and a plane parallel to one of the coordinate planes. Okay, just as a reminder, the coordinate planes are the planes that the XY and YZ and XZ axes go through. So X, Y, Z, this plane right here that the X and Y axis go through, that's the XY plane. Okay, this plane here that the X and Z axes go through, that's the XZ plane. And this plane right here that the Y and Z axes go through, that is the YZ plane. Okay, so we want a plane parallel to one of these planes. And we like the idea of taking a plane parallel to one of these planes because they're really easy to express and because they're really easy to find the intersection of with our surface. Okay, because if I take a plane parallel to one of these, for example, then I could maybe take this plane right here, which goes through y equals 2. Okay, and because it's parallel to the xz plane, x and z could be anything. So the equation of the plane is y equals 2. Okay, that's really nice because that means if I'm finding the intersection of the plane with a surface, that's what I would plug in. All I would do is change all my y's to 2's, and that would give me the 2-dimensional cross section. Okay, let's take a look at an example to kind of get this concrete in our mind. Let's look at the function z equals x squared plus y squared. Okay, and I'm going to show you what this is beforehand so you have an idea. Okay, it's a paraboloid. All right, so what we're going to do is we're going to take some cross sections of this by intersecting it with planes parallel to the coordinate planes. What this means in practice is we are going to look at places where the x or the y or the z values are fixed. I will fix one of the variables. Okay? So if I'm going to look at the z equals 1 plane, that means that I am fixing the value of z to 1. Okay, so if I plug that in here, the cross section, I replace the z with 1, is 1 equals x squared plus y squared. That is something that I could graph easily, right? That is just a circle of radius 1. Let me go over here because I'm going to do a few of these. I want some room. There we go. Circle of radius 1. So that's my cross section when z equals 1. Okay? And so we could see that on the graph. When z equals 1, okay, that's the plane, z equals 1. And I'm looking at the cross section where that plane and the surface intersect. And so I get, hey, look at that. It's a circle, just like I drew. If I take away the two surfaces, you could see, hey, it's a circle of radius 1. Okay? So it gives me, not the full graph, right? I don't, just that circle is not going to do me a whole lot of good. But it gives me one layer. And if I could build up enough layers, I could get a picture of what this surface looks like. Okay, so let's do another one. Let's do z equals 4. Okay, now choosing which cross sections you want, it's a little bit of an art. I look at this and I say, oh, if z is fixed, then that means I'd have a circle. Okay, and so I would want to choose z so that I have a nice radius. And I know 4 is 2 squared. Okay, so that's the thinking that I go through. Okay, so z equals 4. I get 4 equals x squared plus y squared. And again, immediately I say, oh, that's a circle of radius 2. Okay, so if I draw that out, that's a circle of radius 2. I just have to remember that's not z equals 2, that's z equals 4. Okay, so I start at z equals 1, little circle right here, and then at z equals 4, it's just, the radius has just gotten 1 bigger. Okay, so I had to go all the way up to z equals 4 to just increase my radius by 1 unit. Okay, let's do another. I look at this and I say, okay, what z's can I plug in? Well, on the right-hand side, I have x squared plus y squared. That means for sure this side of the equation will be non-negative. Okay, so z cannot be negative. There are no solutions where z is negative because the right-hand side of the equation must be non-negative. So the smallest z could possibly be is 0. So what happens if z is 0? 0 equals x squared plus y squared. So what, that's a circle of radius 0? Well, I mean, kind of. This does have a solution, but we usually don't think of it as a circle. This guy, the only point that would make this equation true is if x and y are both 0. Okay? X and y are both 0, the equation's true. But if x and y are anything else, then because they're squared, I get positives, and I'll be adding two positives together, so it wouldn't be 0. So the only possibility is 0, 0. So I only get a single point when z is 0. So that would be at the origin when z is 0. And so we start to get this picture. Now I've drawn all these layers in 2 dimensions, but we want to visualize them in 3. So you could try drawing them in 3, though it is a little tricky, I'll tell you that. Okay, so let's draw what we have in 3. I have the single point at z equals 0. When I get to z equals 1, I get a circle of radius 1. So something like that. Okay, and at z equals 4, which is way up here, I get another circle. Of radius 2. And so I start to get a picture of what's going on. You can kind of start to see, especially knowing what we know about what we're getting, you can see that we're going to get that paraboloid when we're done. Right? So let's do those other surfaces. So z equals 4. At z equals 4, that was our intersection. Okay, that circle there. Okay, and then at z equals 0, we just hit the very bottom of the paraboloid. And so we just get that origin point. Okay, so you could see how we're building it up so far. Okay, if you're uncertain what a surface looks like, you can always graph more traces. Right? Usually it's a good idea to not focus everything on one variable, but to look in at traces for x and y also. Okay, so I've spent a lot of time looking at the z because I could easily graph those traces. They were circles, and I love graphing circles. They're super easy. But let's look at a couple traces with fixed x and y. Okay, so here's our surface again. So let's look at x equals 0. Okay, 0 is always a good one to pick. Usually you get some nice traces there. Okay, so if I let x equals 0, then the resulting equation is z equals y squared. And so in the zy plane, I'm going to get, well, that's a parabola. Let me actually color it purple. That way I won't clash with the other traces I've already used. Okay, and what about y equals 0? Again, looking at the traces where x, y, and z are 0, usually a good place to start. If I plug in y equals 0, the cross section that I get is z equals x squared. That's also a parabola. But instead of being in the yz plane, it's in the xz plane. Okay, I should probably label this the xy plane. Okay, so let's add those other two in there. So x equals 0, so now I'm in the yz plane. Get that. And if I'm in the xz plane, that would be this plane here. I get the same thing. I just have to be careful to sketch the perspective as best I can. Maybe I'll do it this way so I go through. Okay. Again, if you have enough traces, you can eventually figure out, oh, I know what that is. That's going to be a paraboloid. Now, generally, for these surfaces, you do not need to be exact. Okay? The purpose of drawing these surfaces is not to get an exact representation of the behavior of the equation, but to get an idea of the behavior. And once we know it's a paraboloid, it opens up. That tells us an awful lot without having to... Notice I didn't even label the axes here. I didn't even include tick marks. All I needed was enough information to give me an idea of what I'm working with. Okay? Often that is all you need. So let's go back to our picture, our three-dimensional graph, and we can include those last traces, and you could see in quality better than what I was able to draw what we're dealing with here. So that's the YZ plane. Let me go to the positive axes. There we go. That's the YZ plane. It's intersecting, not that one, x equals 0. Okay. And then our last trace here is where we intersect the XZ plane. That's where y equals 0. And we get another parabola. And so if you put it all together, you really can see that, oh yeah, that's going to be a paraboloid. So by looking at these traces, looking at the different cross sections and then piecing it all together, we can get a good sense of what the ultimate surface will look like altogether. Let's take a look at another example. We have here the equation of some quadric surface. In this case, we don't know what this surface looks like. Unless you're really familiar with quadric surfaces, you don't know what this equation is going to give you. So let's plot some traces, and then maybe we'll have an idea of what we're working with. Okay. So a good place to start, if you're not sure, is try plugging in 0 for x, for y, and for z separately. Okay. So if I plug in x equals 0, I have negative y squared plus z squared over 9 equals 1. If I just swap the y squared and the z squared terms, I get z squared over 9 minus y squared equals 1. That is a hyperbola. And so let's graph it real quick. I'll be graphing this on the YZ plane because those are the variables I have left. All right, it's a hyperbola centered at the origin. I'm going to go 3 units in the z direction and 1 unit in the y direction. There's my box. Get the lines that go through opposite corners. Those are my, give myself a little more room here, my asymptotes. Since the z is positive, I will be opening in the z direction, up and down. And then just draw your 2 parts of your hyperbola hugging the asymptotes. Okay, so looking at the YZ plane, that's what we're dealing with. Okay? All right, let's look at the next plane. Let's look at the plane where y is 0. So if y is 0, that would leave me with x squared over 4 plus z squared over 9 equals 1. So now I'm looking at the xz plane. And here's my x-axis, here's my z-axis. I'm going to move 2 units out in each direction on the x from the center, which is the origin. Right? 3 units in each direction from the center in the z direction. Because I recognize, of course, this is an ellipse. And I know how to plot an ellipse when it's in standard form. And there we go. That is what this is going to look like in the xz plane. Let's graph one more plane. Z equals 0. If I plot z equals 0, I get x squared over 4 minus y squared equals 1. I recognize that equation. That's another hyperbola. So this will be my x-axis. This will be my y-axis. So I'm going to go, let's see, 2 units out from the center, which is the origin. 2 units out from the center in the x direction. Let's use yellow here. And 1 unit out in the y. It's a hyperbola, so I draw a rectangle through those. I draw the asymptotes through opposite corners. And the x is the positive term, so I'm going to open in the x direction. Okay, so this gives us a good start. Let's see what happens when we put these 3 graphs, these 3 traces, into the 3-dimensional space. Okay? X, Y, Z. So I'll start with this in the YZ plane. Nice thing about this in the YZ plane is the YZ plane is the one that's facing us, right? It's this plane right here. And so I just draw the graph as it is. You don't need to be super exact here for most of the time. Just get an idea of what you're doing, okay? So I'm not going to draw the asymptotes. I'm just going to go around 3 up. I'm not even going to sketch the tick marks, okay? And just draw the 2 halves of your hyperbola, okay? For the next graph, it's y equals 0. That's the xz plane. The xz plane is this one here, okay? And it's an ellipse, so I kind of am going through these points. And again, I'm not going to be super careful. Just need an idea of what I'm dealing with here. Okay, and then finally, z equals 0. This will be in the xz plane. This is, or I'm sorry, the xy plane. This is where I need to be most careful. The xy plane is this plane. Okay, but notice the x is coming right towards us. So here, it's a hyperbola, but opening in the x direction. So I want it to open this direction and this direction. And this is pretty tricky because you really have to be careful with perspective here. So I'm going to draw this side shorter and this side longer. And you could see how your picture gets pretty muddled pretty fast, right? Let me just kind of show what's on top here. erasing a little bit. There we go. Okay, so maybe you're having a hard time visualizing what's going on here. Okay, let's add these traces to our 3D graph. That'll help you see what's going on here. Let me pull this over here. Okay, so there's the hyperbola in the YZ plane with x equal to 0. Here's the hyperbola in the ellipse in the XZ plane with y equal to 0. And in the XY plane with z equal to 0, we get the other hyperbola. So if we put them all together, that's what we get. Okay. What the heck is that? So hopefully you could understand my picture a little bit better now that you can see it in 3 dimensions. Okay, that's what we're getting. But are we sure what's going on here? Maybe not. This may not be enough information to get you what you need. Okay, if you need more traces, you can always draw more traces. I recommend that you focus on the traces that are easiest to work with. When I fixed the x and the z to be a fixed value, I got hyperbolas. Hyperbolas are kind of annoying, right? But with y equals 0, I got an ellipse. I like ellipses better than hyperbolas. If I have to draw one, I prefer to sketch out an ellipse. Okay, so I'm going to try different values of y, and hopefully I'll still get a bunch of ellipses. So let's look at this generally. What happens when I fixed y? So let's look at, and I'm gonna not pick a particular value of y. I'm interested in the general behavior and what happens here. What if I set y equal to a constant generally? So I'd get x squared over 4 minus, instead of y, I'm plugging in some other constant. Okay, the goal here is not just to think about one trace, but to think about the behavior of all the traces for fixed y. Okay, let me make sure I copied it down right. I did. Okay, now k isn't a variable, so I'll move it to the other side with the other constants. So I get x squared over 4 plus z squared over 9 equals 1 plus k squared. Okay, I recognize this. This would be an ellipse in the xy plane, right? I just have something that's not 1 over here. So I'd have to divide by this. So x squared over 4 times 1 plus k squared. Z squared over 9 times 1 plus k squared equals 1. Okay, so what I'm doing here is kind of a more advanced technique. Instead of looking at a particular value of k, and I could have plugged in 1 or 2 or 5, okay? What I'm doing is I'm trying to say, generally, what's the behavior here? As I change the y, how does the trace change? And I'm looking at this and I say, okay, this will always be an ellipse, okay? And if I put it in standard form, then I notice that as the k gets bigger, as the constant I'm setting the y equal to gets bigger, how far I spread out in the x direction and how far I spread out in the y direction also gets bigger. I'm getting bigger ellipses, okay? And notice because the k is squared, that's also going to happen in the negative direction also, right? The bigger negative numbers mean I get a bigger denominator here and here. And based on what we know about how ellipses work, that means that I'm going to stretch out more in the x direction and in the z direction as y gets bigger, further away from 0, either in the positive direction or the negative direction. Okay? So that means that I'm just going to get these ellipses. Let me use a color here. that get bigger and bigger, and it'll just stretch out so it always touches the edges of these hyperbolas. Okay. So notice by thinking about it generally, I was able to save myself a little bit of work. Okay. And so as my y goes this way, as my y goes that way, and I look at the trace, I'm just getting larger and larger ellipses. Okay. Hopefully you can kind of see what's going on. Let's put them over here. Okay. So you see, as the y gets bigger, I get bigger and bigger ellipses. In fact, let's set it to k. So you could see that as that k increases, those ellipses just get bigger and bigger. All right. So hopefully you can kind of see what's going on now. We are going to get, let me sketch it out here. When I put it all together, I get a hyperboloid of one sheet. Hyperboloid of one sheet. Let's see that here. Okay, there, you could see the hyperboloid of one sheet. Okay, notice, looking at it this way, I have that hyperbola, right, in the YZ plane. Looking this way, I have a hyperbola in the XZ plane. Let me switch these to, or actually, let me switch this to a different color so we could see things a little better. Nope, wrong one. This one. There we go. In the YZ plane, we have, that orange is really bright, isn't it? Let me do this one maybe. And I think the orange contrasted better. There we go. So you could see right there we have that hyperbola. If we look this way, so we're looking at the XY plane, we have that other hyperbola. Okay, and if we look this way, so this would be the XZ plane with y equal to 0, we have our ellipse. So we really do get all those traces. When we put them all together, you could see that we are getting this hyperboloid of one sheet. Let's do another example. So here we want to sketch the surface z equals y squared over 4 minus x squared. Again, you probably don't have a lot of intuition for what this surface looks like. So we need to sketch some traces to get an idea of how this surface behaves. Okay, again, a good place to start: x equals 0, y equals 0, z equals 0. Let's look at the trace through x equals 0. So if x equals 0, that means my equation becomes z equals y squared over 4. And that is a parabola. So in the yz plane, this will open up in the z direction. Again, center's at where the vertex is at the origin. And if I go 1 out in each direction, I'll only go a quarter up. So very wide opening parabola. Okay, so that's one trace down. Let's do y equals 0. Y equals 0, we're going to get something very similar. We get z equals negative x squared. Again, a parabola. This one, though, in the xz plane, it's going to open down. Okay, so the vertex is at the origin, and it opens down, and the coefficient's -1, so if I go 1 over left or right from the vertex, I will go down 1. Okay, and then finally z equals 0. If z equals 0, I get 0 equals y squared over 4 minus x squared. Now you want to be careful here. If you look just at this side, you might think, I've got a hyperbola. But remember, on the other side of the equation, you need a 1 for this to be a hyperbola, and there is no 1 here. Okay? And there's no way to get a 1 here. So actually, in this case, we do not have a hyperbola. If I move the x squared over, and let's move the 4 over also. So I add the x squared over to multiply the 4 to the other side. I get y squared equals 4x squared. Square root of both sides, y is equal to plus or minus 2x. Okay, so I actually get 2 lines. Sometimes we call an equation like this that looks like a hyperbola on this side, but not on this side, a degenerate hyperbola. So here we have 2 lines with slope 2 and -2. Here's my 2 lines. Here's the line with slope 2. Here's the line with slope -2. And there we go, 3 traces. All right, let's go ahead and embed them into 3-dimensional space. See if it gives it an intuition for what we're going to get. All right. So x, y, z. So this first one with x equals 0, I'm getting the yz plane. Yz plane again is this plane. And I'm just getting a parabola, kind of wide opening. Since the plane is facing us, I pretty much draw what I've already drawn. Something like that. Don't worry about being too exact. We just need a rough idea of what we're getting. For the second one, this is going to be in the xz plane. That's this plane here. So I'm going to draw another parabola, but this one I'm drawing kind of sideways because of the plane it's in. I got to be aware of the perspective. So trying to keep that perspective in mind. If you're like me, you'll try to be a perfectionist with this. In fact, that'll help me No, that's how far I've got to go. Okay. There we go. That's about right. Okay. And then the final one is equal 0. That's going to be in the xy plane. Again, be careful because this x is that axis is this axis, right? So it's narrow together as it goes in the positive y direction. This is a smaller angle than this one. So I want a smaller angle, get the right color, smaller angle this way. Okay, just try to get that perspective correct. Something like that. Okay, that's what we've got so far. And what does that help us with? Probably not a whole lot, right? Just like that. We probably can't look at them and say, oh yeah, obviously that's this. Let me give you an idea though of what we're dealing with so you don't have to just look at my bad picture. Okay, that's what's in the YZ plane. That's that first parabola. That's the second parabola in the XZ plane. Okay, so this is kind of the direction we're looking at in my picture. And then we have the two lines in the XY plane. Okay, so that's what we're dealing with. Not very clear what surface we're dealing with yet, right? So we need more traces. If the picture isn't enough, you need more traces. So I usually pick one variable and then think about how the traces change as we change that one variable. All right, so which variable would I pick? Well, z is kind of nasty because if z0, I get a degenerate parabola, but if z was 1, I'm sorry, a degenerate hyperbola. But if z was 1, I would get a hyperbola. Hyperbolas are kind of unpleasant to sketch. I could do it if I want to, but I don't. So if there's something easier, that'd be better. Okay. This one seems best. I like this one because right now, this is nice and simple. I don't have any gnarly denominators to work with. Okay. So this one's probably my favorite to work with. I'm going to change the y. I could have done this one too. It's not that much harder. But just because this has a denominator, I'm going to go ahead and work with this one. Okay. So I'm going to do similar to what I did last time. I could plug in one number at a time. But instead, I'm really interested in how this changes as I change the value here, how the trace changes. Okay. So let's plug in y equals some constant k. And then I want to think about what happens as I change that k. So if I plug k into the y here, that was what? Z equals y squared, which I'm plugging in k, over 4 minus x squared. All right? Yeah. So now k is a constant. The only variables are z and x. Okay? And I'm just going to write this a little bit different just to emphasize that this is mostly what's going on. That's what's going on. And then I'm adding to that k squared over 4. Now, how does that extra addition of a number affect things? Well, thinking about shifting, adding something over here, that's going to shift things up. I have a parabola that opens downward, and then adding a number shifts things up. The bigger k is, the bigger this number will be, the bigger the shift will be. Okay? It's squared, so it doesn't matter if it's positive or negative, both. If it's a big positive number or a big negative number, it's going to shift the parabola up. Okay, so the bigger y is, the more positive I go on the y, the more negative I go on the y. This downward opening parabola goes further and further up. Okay? So it's just like this parabola here, but as I go on the y, and you kind of want to hug what you already have, so I'm going to go this, this, this. as I go on the y, I go further and further up. Okay, so it's hitting these points, hitting these other traces. And in the other direction too. As the y goes further in the positive direction, further in the x direction, I just take that parabola, same parabola, the z equals negative x squared, and I'm just shifting it up. It's a very good one. Keep on going. One more. Okay. So hopefully you could kind of see what's going on now, more or less. And it'll help if I recreate it here. So let's actually take this one. Do I have a purple? I do. And I want y equals k. Okay, so as in fact, let's just animate it. So it will trace out that path. Okay, and you get an idea what's going on. And if you're still not sure, you could always do the other parabola too, right? Let's do it just so we could see, because maybe you're still a little bit uncertain what this looks like. You're starting to get an idea, but you're a little uncertain. Let's do the same thing here, okay? Here I've chosen x equals 0, but what happens if I let x be some constant, and I'm interested in what happens to the trace as that constant changes? So let's try setting x equal to k. If x is some constant, then I'm going to plug that k in for this x. So I get z equals y squared over 4 minus k squared instead of minus x squared. Okay, this part is the same parabola as up here. Okay, that same parabola. But as I let the value of x change, as I change the x plane that I'm looking at, I change this value. Okay, so I'm subtracting k squared. As x gets more positive or more negative, this gets bigger. And so I'll be subtracting a bigger and bigger number. That's going to shift the parabola down so it's lower on the z-axis. Okay? And I don't know if I want to draw it here because it'll look too busy, but it's still the same parabola opening up. Okay? Now I'm hitting all these points. As the x gets bigger, as I go further in this direction, and as I go further in this direction. I think I really don't want. Let me try it. And that's really back there. I don't know if that helps things or not. Okay. Now I want to emphasize one more time. This, you may be looking at this and say, goodness gracious, that's a big mess. I can't make heads or tails of that. The purpose of these drawings, I'm doing the best I can here, but when you do it on your own, the purpose of these drawings is not to give a perfect representation to everyone of what this is. This is a tool for you to use to help you get a picture of what this is in your mind. Okay, and I've been drawing enough now that I have a pretty good idea of what I'm dealing with here. It does help if you know some of the basic quadric surfaces and the shapes that could happen. Okay, And before I draw it out, let me make the same kind of picture here. Same trick. I'll just set this equal to K. And yeah, red's good. Let's play it. Okay. So that kind of traces out the edges of this quadric surface. So what we end up getting something like this. Okay. This is a hyperbolic paraboloid. Or sometimes we call it a saddle for obvious reasons, right? It looks like a saddle. That's what we're getting here. Can you kind of see it now? Let's put it here. Let's just get rid of this. Okay. There we go. Let's look at each trace one by one so we can really see what's going on here. So there is the parabola we got from setting x equals 0 in the yz plane. Okay. Here's the trace, the parabola down here, set in y equals 0 in the xz plane. Then we have that degenerate hyperbola. Those two lines. Can you see that? Okay. And actually, if you change z, if you raise it up a little bit or lower it down a little bit, you will get a hyperbola. This is kind of in the middle where hyperbolas change. If you go lower, you could see that there's a hyperbola opening up and down here, right? And if you go higher, you have a hyperbola opening left and right. Okay. And then we have these other parabolas. This is the general behavior we saw as we went further away from 0. That downward opening parabola got higher, right? It shifted up. So the more negative we got or the more positive we got, the more shifted up that parabola became. Okay, and same thing with this one, just in the opposite direction. This one is a upward opening parabola, but as we went in the positive x direction or the negative x direction, that same parabola just shifted down. Okay, so it does take some practice to get these down and to understand. I will not test you on getting in drawing these perfectly. I will test to see if you can understand how to take a trace and then use that to identify a surface. But I won't be testing you on your drawing skills in this class. I want to take a look at just one more example. This example is a little different because this one is not a quadric surface. And so I wanted to emphasize that this technique that we're learning, how to use traces to help us sketch a surface, it can help us sketch really any surface, not just quadric surfaces. Okay? So we're going to do exactly the same thing that we've done before. This one's not a quadric surface, though. The giveaway, by the way, is the x's and y's in the denominator. You can't have x's and y's in the denominator in a quadric surface. Okay? Let's see what we get here. Same trick as before. I'm going to start with x equals 0, y equals 0, z equals 0. Okay? So x equals 0, I get z equals 3 over 1 plus y squared. So what's that going to look like in the yz plane? This one's a little trickier, right? Because it's not a conic section that we're really familiar with, right? We know conic sections. This is not a conic section. So what's going to happen here? So we've learned some techniques from Calculus 1 about how to graph functions like this. But let's see if we could get some intuition on this without going through all that work. Okay. First off, notice that z will always be positive, right? No matter what y I plug in here, y squared is positive. So I have a positive number on top, I'll have a positive number on bottom. It's positive. And in fact, it will never be 0, right? So z can't be 0. There's no y that I could plug into the denominator that will turn this into 0. But the bigger y is, the bigger the denominator is. So as y gets bigger, z approaches 0. Okay, so we have some asymptotes. The bigger y is, we approach 0. Okay? Now what happens is y gets smaller. The smaller y gets, the closer the denominator gets to, in this case, 1, right? We can't go lower than 1. But the smaller y gets, the closer this gets to 1. As y gets smaller, the denominator gets smaller. A smaller denominator means a bigger fraction. So this gets bigger as y gets smaller, and its biggest value is when y is 0, which will be what, 3? So 1, 2, 3. And so just keep everything nice and smooth. I like how I'm drawing it. Okay, and again, we don't need to be exact. We just need a rough idea. And this is a rough idea. This is fine. Okay, this is what we would expect. Something like that. Okay, little hill. And then approaching 0 as we go towards the edges. Okay, as we try towards infinity. Right? And if we set y equal to 0, let's do the other trace now. Y equal to 0. We get z equals 3 over 1 plus x squared. Hey, those are the exact same equations. I just swap out x for y. Right? So I'll get the exact same trace, just in the xz plane instead of the yz plane. Okay, so far so good. Now let's set z equal to 0. Now, we already kind of mentioned this. I can't set z equal to 0, right? If I set z equal to 0, then I get 0 equals 3 over 1 plus x squared plus y squared. I'd have to pick something, an x and a y, so that what I plug in for x and y here in the denominator turns this fraction into 0. Okay? The only fractions get smaller as the denominator gets bigger, but to be infinitely small, that means the denominator would have to be infinitely big. And I can't actually reach infinity, right? So this has no solution. There's no x and y I could plug in here that's going to make this work. Okay. If you want a little bit more convincing, if I multiply both sides by the denominator, on the right-hand side, these guys cancel. I just get 3. On the left-hand side, 0 times this is just 0. And so what the math is saying is that, oh, you want to know the solution when z equals 0? Okay, the solution, we're going to get a solution whenever 0 equals 3. But 0 doesn't equal 3. That doesn't make sense, right? So no solution. Okay. So let's look at other values of z that could work. Okay, so instead of z equals 0, let's do z equals k. I really don't want to mess with these guys. Okay, and actually fixing z, that x squared and that y squared, that looks nice. We like x squareds plus y squareds because that's where we get circles and ellipses and things. Okay, so maybe something nice will come of that. So let's set z equal to some constant k, and we're interested in what happens as k changes. What are the possible values of k? All right, so we have k equals 3 over 1 plus x squared plus y squared. I don't like my variables in the denominator there, so I'm just going to flip both sides of this fraction. This is really k over 1. So if I flip both sides of the equation, I get 1 over k on the left and 1 plus x squared plus y squared over 3 on the right. Multiply 3 to the other side. That's 3 over k equals 1 plus x squared plus y squared. Now this is starting to look good. I've got the x squared plus y squared, and they're in the numerator. Let's move that 1 to the other side. 3 over k minus 1 equals x squared plus y squared. Okay, and now this looks a lot like x squared plus y squared equals r squared, where this is the r squared, right? So this has the structure like a circle, right? But I need to make sure that this as r squared is going to work out. Notice r squared has to be a positive number, right? Has to be positive to make that work because this side has to be positive. X squared plus y squared has to be positive. So what are the possible values that I could choose for that k to make this work? Well, I can't have k any smaller than 0, right? 0 doesn't work because you can't have 0 in the denominator. And if k is negative, then that means this guy's negative. Minus 1 stays negative. And I know this side can't be negative. So k has to be greater than 0. Okay, and then what's the biggest value I can choose? Well, the biggest value is 3, because anything bigger than 3 would make this fraction smaller than 1. Something smaller than 1 minus 1 is negative, and I need this to stay positive. So that k has to be between 0 and 3. The possible values of z for this equation always have to be between 0 and 3. Okay? But as long as k is within that range, then we have a circle. Okay? As k gets bigger, this fraction gets smaller, and the radius gets smaller. So what that means is for small values of k, we have a big circle. Okay, k just a little bit bigger than 0. And then as k gets bigger, this gets smaller. Okay, so as k or the z value gets bigger, the circle gets smaller, the radius gets smaller, until at 3, it kind of evaporates and goes away. All right? So if we kind of put together what we have, just roughly, okay? here, that's the YZ plane. That's this plane here. We have something that looks roughly like this. Okay. Going in the other direction, in the XZ plane, we have the exact same structure, just in the other plane. Okay. So exact same structure. Reference. Okay. And then Z has to be positive. That's kind of what we looked at. And I didn't draw it super well. Maybe I'll just draw it by hand. And we get circles for different values of Z. The lower the Z value, the bigger the circle. Okay. As we go up, we have these smaller circles. Okay, so you get a pretty good picture of what we have going on. Okay. And as usual, let's take it to Desmos just so you don't have to suffer through my poor drawing skills. Okay. There is oriented the right way. Oh, that was oriented the right way. There is the level curve when we set x equal to 0. Okay, or the trace rather. The trace when we set x equal to 0. We get the same thing when we set y to 0. Let me match the colors in my drawing. And then if we look at the level curves of z, for negative values of z, there's nothing there. Okay? Even for z equals 0, nothing. But as soon as we go bigger than 0, then we start having circles. Okay? And as z gets bigger, those circles get smaller until there's no circle left. Right at 3. And so I'll just show it here because it's kind of hard to draw in more than what I've done already on the here. Actually, I'll try it. Let me give it a try. And so we just kind of have this mound. Okay. That gets with the tip of the mound at the along the z-axis, and just gets bigger as we go down. Okay, so let's see it here. There it is. There's our mound. Okay, and it does match all the level curves we've looked at. So this approach, using traces to understand and gain intuition on a surface, it works for any surface, not just quadric surfaces.